Welcome to AI Paper Slot. Today we are looking at a paper called CODA, Rewriting Transformer Blocks as GEMM Epilogue Programs, by researchers from MIT, Princeton, Together AI, and Meta.
Right, and for the AI researchers and ML engineers listening, we want to give you the bottom line right up front.
Yeah, the core insight here is that as we shift to low-precision formats, your FP8 and FP4 matrix multiplications are getting incredibly fast.
Which is great, but it means memory bandwidth is becoming the ultimate bottleneck in your training stacks.
Exactly. Operations like RMS Norm, SWIGLU, and ROPE are spending most of their time just moving data in and out of global memory. So this paper introduces CODA, which is a GPU kernel abstraction.
And what it does is it algebraically rewrites nearly all of your non-attention transformer computations. It forces them to execute directly inside the epilogue of a GEMM.
Right, while the data is still sitting right there on chip. And it does this by providing 5 composable epilogue primitives.
Which is huge because it allows both humans and LLMs like Claude Code actually to write fused kernels that match or beat highly optimized libraries like Flash and Fur and Lager kernels.
Yeah, it completely eliminates that materialization bottleneck in both the forward and the backward passes.
It is a really profound shift, in how we approach optimization. We are so used to thinking about model architectures as just abstract mathematical graphs on a whiteboard.
Right, just drawing boxes and arrows.
Exactly. But this paper forces you to look at the exact physical layout of the silicon on a GPU, and you have to change your math to fit that physical reality.
So if you're out there optimizing models or wrestling with cluster performance, you definitely feel this pain daily. Let's dissect what actually goes wrong when standard frameworks compile transformer layers.
Yeah, the paper points to a Torch Titan benchmark that really illustrates this perfectly. They were training a Lamame 3-style 1B model on a single H100.
Okay.
And when you drop down from 16-bit precision, like BF16, to FP8, those tensor cores they chew through the math at blinding speed.
Right. The matrix multiplication is basically instant.
Yes. So suddenly, the percentage of your total GPU time that's spent on non-matrix multiply operations, your activations, your residual updates, reductions, it takes up a shockingly non-trivial fraction of the runtime.
It's like Amdahl's law, just hitting you right in the face.
It's a textbook example of it. You optimize the heaviest part of the workload, and suddenly the data movement that you previously ignored becomes the dominant bottleneck.
Right.
And the root cause here is what we can call the framework trap. High-level frameworks, like PyTorch, they represent models as a sequence of discrete operators.
Which is fantastic for autograd and, rapid prototyping. You can swap layers in and out super easily.
It is, but under the hood, those operator boundaries inherently become materialization boundaries.
Which brings up a wildly inefficient analogy. It's like PyTorch is a chef who chops an onion, puts it in a Tupperware container, walks all the way across the kitchen to put it in the fridge.
Ooh, I like this.
Closes the door, and then immediately opens the fridge back up to take that exact same onion out for the frying pan.
That is exactly what happens. Those trips to the fridge are global memory round trips.
Right. You compute this massive matrix multiplication, write the output to the GPU's high bandwidth memory, and then PyTorch launches a tiny separate activation kernel just to read that massive tensor right back in.
Apply a simple SWIGLU activation and write the whole thing out again. You pay this massive latency and bandwidth tax just to, as you said, move the onion.
So to understand CODA's solution, we need to look at the basic anatomy of a high-performance GPU kernel.
Right, which is generally divided into 2 phases. First, you have the main loop. This is the heavy matrix multiply accumulate happening deep inside the tensor cores.
The actual math.
Exactly. And second, you have the epilogue. That's the code that takes that freshly computed output tile, transforms it, and writes it out to global memory. What's fascinating here is that custom kernels written by infrastructure teams, systems like VLLM or SGLang, they already avoid these memory round trips.
By hand-fusing operations directly into that epilogue phase, right?
Yes. But the problem is that doing so requires brutal, low-level CUDA engineering for every single variation of a model.
It's just not scalable.
No, not at all. CODA is seeking the holy grail here, the raw performance of bespoke custom kernels, but with the programmability of high-level building blocks.
Okay, let's unpack this, because I can hear the pushback from our listeners already. Wait, isn't an epilogue usually just for basic stuff?
Like adding a bias vector.
Yeah, exactly.
Yep.
Or scaling the output before you ship the tile off to memory. How on earth are we doing complex full-layer operations like an entire SWIGLU or cross-entropy just using local tiles in an epilogue?
That skepticism is totally warranted. Writing custom CED for every model variation is a nightmare, so CODA has to standardize the process. And it does this by heavily constraining what the programmer is actually allowed to do.
Okay, so it puts you in a sandbox.
Exactly. CODA fixes the high-performance GMM main loop completely. You do not touch the matrix multiplication code. You are only allowed to program the epilogue.
Interesting.
And that epilogue operates under a strict locality constraint. When it runs, it only sees the local output tile that the main loop just computed, its accumulators, and consistently indexed auxiliary tensors.
So there's absolutely no arbitrary global communication allowed. You can't just talk to the rest of the GPU.
None. You cannot synchronize across the whole grid of the GPU.
Which makes perfect sense when you think about it. If you introduce grid-wide synchronization, you force all the streaming multiprocessors to wait for each other.
And that completely destroys the pipelining of the GMM itself.
Right. So if you are locked in the straitjacket, what tools does Gokey actually give you to build a layer?
They give you a toolkit of 5 strict classes of primitives. If you are building a layer from scratch, the first thing you need is a way to handle residual updates or basic activations. For that, you use element-wise and pairwise maps.
Okay, so that covers switch LU and things like rotary positional embeddings.
Exactly. Then what about normalization? A norm weight is just a 1D vector that you need to broadcast across the hidden dimension.
Right.
For that exact scenario, you have the second tool, vector loads and stores. This lets you pull in a row or column vector and broadcast it over the output tile.
Okay, and to actually pull in the residual stream or save activations for the backward pass.
You use the third primitive, tile loads and stores, which lets you read or write full matrix tiles.
Got it. And since normalization requires finding the mean and variance, you obviously need reductions.
Precisely why the fourth primitive is tile reductions. This lets you compute partial reductions over rows or columns of a local tile.
Nice.
And finally, if you are computing something like an online log sum X for cross entropy, you need to track running statistics. So the fifth primitive is stateful transforms,
Which are designed specifically for maintaining those running stats across operations.
Yes.
But, even with those 5 primitives, you still hit a mathematical wall. And this is where the paper really blew my mind. Because CODA isn't just taking existing PyTorch code and jamming it into an epilogue.
No, it mathematically reparameterizes the transformer to fit the physical hardware.
Yes. This is the core insight of the entire paper. Let's look at the classic pattern in a transformer block.
Right. You have a GMM, followed by a residual addition, then an RMS norm, and then the next GM.
A projection, a norm, and the MLP gate. The problem with RMS norm is that it requires calculating the root mean square across the entire hidden dimension.
And that hidden dimension is much larger than a single compute tile.
Way larger. So normally you have to wait for the entire first GM to finish, write the whole massive tensor to memory, run a global reduction to find the root mean square, apply it, and only then can you start the second GMM.
It's a huge traffic jam. But CODA elegantly breaks that dependency by splitting the reduction. In the epilogue of the first GMM, it computes tile local partial reductions.
Okay.
Then, a tiny auxiliary kernel quickly combines those partials across the tiles to get the final row-wise scale factor.
The dollar value.
Right. But here's the genius part. Normally, you apply that scale factor to your activations before you do the next matrix multiplication.
Yeah, that's standard.
Well, CODA mathematically proves you can slip that scalar completely past the next set of weights. Because it's a scalar for a given row, the rules of linear algebra dictate you can just pull it out of the multiplication.
Wait, so you commute the taller scalar past the dollar on a weight matrix?
Exactly. You compute the projection for the second GMM using the unscaled inputs. Then you apply the normalization scale at the very end in the epilogue of the second GMM.
Right before the tiles hit global memory.
Yes, it perfectly fits the hardware's capabilities.
You completely bypass the dependency. The scale factor doesn't act as a gatekeeper before the multiplication anymore.
And doing it this way actually improves numerical accuracy, believe it or not.
Oh, wow.
Yeah, they benchmarked this on a Llama 3 8B layer, comparing the standard PyTorch path to this CODA reparameterization. By keeping these operations fused in the registers and accumulating the math in higher precision before the final cast to memory, you avoid rounding errors.
Because you aren't constantly writing to memory and reading it back in lower precision. That is incredible. And this spatial approach fundamentally changes how we handle activations, too.
Right. Take SWIGLU or ROPI. These are pairwise activations, meaning they consume adjacent feature values. SWIGLU takes a tensor, splits it into a gate and a value, applies a function, and multiplies them.
And a naive implementation materializes the GMM output, splits it, and actually expands the memory footprint before reducing it back down.
But on the newer Hopper architecture GPUs, the tensor cores hold tuples of adjacent values directly in their hardware registers.
Okay, so CODA maps these pairwise activations directly to those register tuples.
Exactly. The expanded intermediate tensor that SWGLU creates exists only in the registers of the streaming multiprocessor. It never touches global memory.
It's like our chef doing the chopping, the seasoning, and the sautéing all in the exact same pan without ever dirtying a cutting board.
Or walking to the fridge.
Yeah.
And you see a similar philosophy applied to cross-entropy using the cut cross-entropy method.
Right. Instead of computing a massive memory-bound softmax over the entire vocabulary, which, could be 32,000 logits or more.
They select the indexed logits using the target label and accumulate the log sum XP statistics locally within the tiles. A tiny auxiliary kernel just swoops in to finish the job later.
Here's where it gets really interesting, though, because I was tracking with all of this for the forward pass. High-performance inference engines already do a lot of forward pass fusion.
True.
But for training, AutoGrad usually shatters these optimizations completely.
Oh, yeah. The backward pass is a totally different beast.
The chain rule requires you to save intermediate tensors, and the backward gradients usually demand entirely different kernel structures. So how does CODA maintain this tight GEMM Epilogue structure when the gradients start flowing backward?
This is where they introduce Theorem 1 in the paper. It proves that forward tile local epilogues induce backward tile local epilogues.
Do some.
Yeah. If you apply a function element-wise in the forward pass, the chain rule states that the gradient update involves multiplying by the derivative of that function. Because it's element-wise, the Jacobian matrix is diagonal.
Okay, FL.
Practically speaking, this means that during the backward pass, multiplying by that derivative can simply happen in the epilogue of the backward GEMM that computes the gradient.
Oh, so the structural boundary stays exactly the same. You just run the fusion in the opposite direction.
Exactly.
Hold on, let me play devil's advocate here. I get that for element-wise functions, but RMS Norm isn't element-wise. RMS Norm backward is notoriously brutal.
It is.
Normally, calculating the backward pass for RMS Norm requires a row-wise inner product of the forward activation and its gradient. That inner product forces you to launch a standalone, memory-heavy kernel just to read those massive tensors back.
You've identified the exact bottleneck. To find the gradient, you need to compute the sum across the columns of the gradient of the activation, multiplied by the activation itself. Let's call the activation $22.
Okay,
Reading $2 back from memory is painfully slow. But CODA uses a beautiful mathematical identity to avoid reading $12 entirely.
Wait, really?
Yes. We know the next operation in the forward pass was multiplying $8.2 by the weight matrix. And the gradient flowing back is simply the gradient of the output multiplied by the transpose of that weight matrix.
Right, standard backprop.
If you substitute that into the inner product, the math simplifies drastically. The row-wise statistic you need is mathematically identical whether you compute it using the activation $2 or the output of the next layer.
Wait, run that by me again. Instead of launching a new kernel to read the activation in its gradient, CODA computes the statistic using the output of the next GMM block.
That is the identity hack. They accumulate this row-wise statistic at the boundary of the adjacent GMM block. That's where the pre-epilogue tensor and its gradient are already sitting hot in the registers.
You are quite literally using the output of the next layer to compute the statistics needed for the previous layer's norm gradient. That is absolutely wild. The dependencies flow perfectly if you just shift your perspective one boundary over. You completely eliminate the standalone activation-sized RMS Norm backward kernel.
It just vanishes into the epilogue of the adjacent GMMs.
Wow. So let's talk about the human element here. What does this all mean for the engineers actually writing the code? Because all these algebraic reformulations are brilliant on paper, but writing the code to implement these Hopper-specific register manipulations is incredibly complex.
It's very tedious.
Yeah, for those who haven't suffered through it, they are using CUDA, which is this deeply complex templated C++ library. I wouldn't want to hand code that.
You wouldn't want to, and with CODA, you might not have to, because the system is explicitly designed for LLM-assisted authoring.
Which is a bold claim, because asking an LLM to write raw, highly optimized CUDA from scratch usually ends in disaster.
Almost always. Raw CD gives you thousands of threads, complex grid dimensions, shared memory banks. The search space is too massive.
The LLM hallucinates memory strides, it invents synchronization barriers that cause deadlocks. You get race conditions everywhere.
Yes, the unconstrained search space of raw CUDA is exactly why LLMs fail. But CODA gives the LLM, in this case, they used Claude Code, a sandbox.
Ah, the primitives.
Right. It provides those heavily constrained, pre-optimized, composable building blocks we discussed earlier. The LLM doesn't have to figure out how to write a deeply complex memory load or a Hopper warp reduction.
It just has to logically compose the 5 CODA primitives to match the algebraic reparameterizations.
Exactly. The constraints of the epilogue physically prevent the LLM from hallucinating those grid-wide sync barriers.
And the benchmarks actually back up this approach. They tested this across hidden dimensions representing typical model scales, specifically dimensions of 2048, 4096, and 8192.
Which represents roughly your 1B, 7B, and 70B parameter models.
Right, and both the human-written CODA kernels and the Claude Code LLM-written CODA kernels either matched or outperformed state-of-the-art handwritten libraries.
We are talking about beating Liger kernels and flash infer on operations like the full GMM RMS Norm swidgel U block.
And completely blowing standard PyTorch with couplets out of the water.
Oh, absolutely. And for the backward pass, where standard PyTorch really suffers from memory bloat because it's saving all those intermediate tensors, CODA showed massive speedups, up to 1.7x faster on the backward pass.
That is just huge for training efficiency.
This raises an important question, though, about the future of compiler systems as a whole.
How so?
Well, for years we've relied on general-purpose graph compilers like Torch Inductor or XLA to magically look at a PyTorch script and fuse operations.
Right, you just trust the compiler to figure it out.
But as hardware gets more specialized, like the register tuples on Hopper or the new specialized tensor memory on the upcoming Blackwell chips, general compilers struggle to find these highly specific hardware math alignments.
They just can't see the optimal path.
Exactly. What CODA proves is that giving LLMs constrained domain-specific hardware primitives might be the future of auto-generating highly efficient systems code.
So you don't need a massive monolithic compiler to guess the optimal fusion strategy if an LLM can just intelligently compose known good epilogue primitives based on a mathematical proof.
Yes, it is shifting the burden of optimization away from a rigid compiler and handing it to an agile, mathematically aware LLM working within a safe, deterministic sandbox.
Let's bring this all together for everyone listening. The core takeaway here is that looking at model math through the lens of hardware constraints changes everything. By mathematically reparameterizing operations like RMS Norm and swidgel so they can live entirely inside the GEMM Epilogue, CODA removes the global memory bottleneck.
It literally unchokes our modern low-precision tensor cores.
It does it beautifully. Be sure to subscribe to AI Paper Swap on YouTube so you don't miss our next breakdown. We summarize the heavy AI and tech papers so you can stay up to date with the latest research.
Before we wrap up, I want to leave you with a thought to mull over. If we can algebraically reformulate transformers specifically to hide their memory-bound operations inside GMM epilogues, what does this mean for the future of model architecture itself? Should researchers stop designing architectures on whiteboards in a vacuum?
Oh, wow. And start co-designing them directly alongside Hopper and Blackwell register layouts.
Exactly. What if the next great LLM architecture isn't discovered by theoretical elegance, but is just whatever math happens to fit perfectly into a tensor core's epilogue?
That is a fascinating thought. It is the ultimate engineering reality. If you design a recipe where the chef never have to walk to the fridge, the kitchen can output 10 times the food.
Keep the onion out of the Tupperware and keep your activations in the registers.
I love it. Keep optimizing, everyone, and we will see you next time.